Welcome everyone. It is an honor to present my research on one of the most essential topics in modern cloud computing. My name is Ammar Nabil Shahi, and the work I am sharing with you today is titled Load Balancing in Cloud Computing based on ant-colony optimization and cross-search algorithm. This research was developed at the School of Computer Science and Technology, University of Science and Technology of China, Hefei Hui. It represents a step forward in addressing how we can balance workloads in cloud system to achieve greater efficiency and reliability. Let's embark on this journey together. Let me walk you through the outlines of this presentation. We will begin by discussing the introduction and the motivation behind this research, highlighting the challenges in cloud computing, load balancing, and why this topic is critical. Next, we will dive into the related work to understand the existing solution and identify the key gaps that the research addresses. After that, I will present the system model and the proposed hyper algorithm SEO-CSA, explaining how it combines the strength of the anti-colony optimization and cross-search algorithm to achieve better performance. We will then move to the experimental setup and the results, where I will share how the proposed algorithm was tested and compare its outcomes with other states of the art methods. Finally, we will wrap up with the conclusion and the future directions, summarizing the key findings and outlines potential areas for further exploration. Let's dive into each point to uncover the details of this research. Introduction and research motivation. Cloud computing includes delivering essential computing service like server, storage, database, networking, and software over the internet. This makes these resources easily accessible from any location, enhancing flexibility and efficiency. Load balancing includes distributing tasks across various computing resources to prevent any single resource from becoming overloaded. This optimizes resource utilization, enhancing system performance by reducing response time and cost by balancing workloads effectively. Virtual machines help optimize resource use by running multiple operating systems on a single machine. Quality of service measures how well cloud services perform in terms of response time and reliability. In our research, we use two algorithms. The first one, SEO, that helps in finding the best paths for resource management by mimicking ant behavior, while the second algorithm, CSA, enhances resource allocation by imitating how crows store and retrieve food. Efficient load balancing is crucial in cloud environments to address their grounds complexity and ensure cost-effective operations. By using SEO, we can distribute tasks more effectively, reducing response time. CSA improves this by ensuring tasks are allocated efficiently, leading to better overall performance and resource utilization. Our research addresses critical gaps in existing load balancing methods in cloud computing. We introduce Hyper SEO CSA algorithm combining SEO and CSA, which improves load balancing by reducing response time and computational cost. This approach enhances resource efficiency and adapts to dynamic changes in cloud environment. One of the biggest issue in cloud computing is uneven workload distribution, which leads to inefficiency and delays. Overloaded servers waste energy, and managing this imbalances in real time adds more complexity. As the demand for cloud service grows, scaling system becomes harder. These challenges are what drive the need for better solution, which we will explore next. The motivation behind this research arises from the increasing dependence of cloud computing service across various sectors. As demand grows, it becomes essential to optimize the use of available resources to improve efficiency and ensure faster response time, enhancing user satisfaction. Furthermore, current methods often face limitations and inefficiencies, leading to higher operational cost. This research seeks to address these challenges and provide effective solutions to meet the evolving needs of cloud computing systems. This research introduced three pivotal contributions to address critical challenges in cloud computing: load balancing. First, we design precise objective function to optimize response time and computational cost, ensuring efficient task assignment within resource limits. Building on this, we proposed a hyper algorithm ACO-CSA, which intelligently combines ant colony optimization and crow search algorithm. This innovative algorithm leverages the strength of both techniques, balancing exploration and exploitation, to achieve outstanding results. Finally, we implemented and rigorously evaluated ACO-CSA, demonstrating its ability to reduce response time, lower cost, and enhance fairness. Across resources, these contributions collectively represent a practical and scalable solution to improve cloud computing efficiency. To summarize the contributions visually, our research flew a structured flow. We began by designing an objective function to ensure resource efficient task location while minimizing response time and cost. Next, we introduce ACO-CSA, a hyper algorithm that combines the best of ACO and CSA to achieve balancing and optimized solution. Finally, we implemented and tested the algorithm extensively, achieving significant improvements in response time, cost, efficiency, and scalability. This systematic approach demonstrates how the research biggest existing gaps and offers innovative solutions to dynamic challenges in cloud computing. Related work and gaps. Extensive research has been conducted on load balancing algorithms. They can be classified into main categories: meteoristic algorithms like Lewis and GWO are inspired by natural processes, while hyper algorithms like RAFL combine multiple techniques for better efficiency. Traditional load balancing techniques face issues like inefficient use of resources, leading to high response time and poor adaptability in dynamic environments. Despite their advantages, meteoristic load balancing algorithms have flaws such as unpredictable results from random initializations, begin resource intensive due to high complexity, delayed outcomes become because of slow convergence and limited flexibility in handling dynamic workloads. System model and proposed algorithm. In this section, we present the primary focus of our research, which is developing a hyper algorithm for load balancing in cloud computing. This solution integrates SEO and CSA to address challenges in dynamic cloud environment. Our proposed algorithm aims to solve the load balancing challenges in cloud computing by designing an efficient resource allocation strategy. We evaluate its performance based on response time, cost, and fairness in load distribution, ensuring optimal use of cloud resources. This slide illustrates our research methodology, the process, and involves four main steps: tracking virtual machine loads, updating foreman trails to improve task assignments, detecting load imbalances, and dynamically redistributing tasks using the hybrid SEO-CSA algorithm. This slide illustrates the proposed system model for load balancing in cloud computing. The model focuses on task allocation within a physical machine, where tasks are distributed among virtual machines under the same physical machine. This approach includes intra-physical machine task migration to optimize load distribution and resource utilization, ensuring improved performance and reduced delays. On this slide, we present the problem formulation, which outlines our objectives and constraints. The primary goal is to distribute tasks across virtual machine, effectively ensuring load balancing, minimizing response time, and optimizing resource utilization. The problem is modeled using a Linear objective function, which incorporates three key aspects: response time, cost, and fairness. In load distribution, the constraints include signal task assignments per virtual machine, adherence to resource limits, and maintaining load balance across all machines. Result and analysis. Let me now show you the results obtained. Starting from the figure 2 shows the cost performance of ACU and CSA. Both algorithms have fluctuations indicating their efficiency is different with task complexity and the number. This shows they are cost effective and adaptable in managing the resources. Figure 3 compares the response time of ACU and ACU CSA. As the number of tasks increases, ACU CSA keeps lower response time. This shows ACU CSA is more robust and efficient in handling large workloads compared to ACU. Figure 4 illustrates comparative analysis of the average response time for each algorithm across various task sizes, highlighting ACU CSA's superior performance leveraging its hybrid approach. ACU CSA consistently achieves shorter response time, particularly for large-scale tasks, outperforming other algorithms such as MLVM, BAVM, and GIGA, and demonstrating its efficiency and scalability in dynamic environments. Figure 5 provides a comparison of the average compilation time across various algorithms, showcasing SUCSA's superior performance. SUCSA consistently achieves shorter computation time for all task size. For all task size, completing 100 tasks in 46 seconds compared to 51 and 53 seconds for GIGA and AOA, respectively. This highlights SUCSA efficiency in optimizing task processing and its scalability in handling large workloads effectively. The table compares task computation times across 10 algorithms, highlighting SUCSA's superior performance. SUCSA consistently achieves the shortest computation time, completing 100 tasks in 300 seconds compared to 410 and 330 seconds for GIA and BAVM, respectively. This demonstrates SUCSA efficiency in handling large workloads, reducing response time, and optimize resources utilization, making it an ideal solution for dynamic and high demand environments. Figure 6 demonstrates the fairness improvement achieved by the optimized SUCSA algorithm, increasing from 86 to 89.5 over 100 iterations. This highlights its effectiveness in evenly distributing load across virtual machine, improving system efficiency. Conclusion and future direction. This research introduced the hybrid SUCSA algorithm to optimize load balancing in cloud computing environments by combining ACO and CSA. The algorithm demonstrates superior performance in minimizing response time and cost compared to conventional methods. Despite these advancements, limitations remain, including the uh, computational resources required for implementation and the dependency on parameter fine tuning. Future work should focus on integrating additional QoS metrics such as reliability and security, and developing adaptive mechanisms to enhance the algorithm's flexibility and applicability in dynamic cloud environments. Thank you all for taking the time to go through my presentation. I hope the content was insightful and provide valuable information. Please, if you have any questions or need further clarification, please feel free to reach out to me. I will be happy to assist you. Thank you so much.